Welcome! In this session, we will explore the problem minimum time to complete trips. We'll break down the problem statement, examine potential solutions, and discuss the key insights behind solving it effectively. Let's dive in. In this problem, we are tasked with determining the minimum amount of time required for a group of buses to collectively complete a given number of trips. We are provided with an array time, where each element represents the time it takes for a specific bus to complete one trip. Additionally, we are given an integer total trips, which specifies the total number of trips that need to be completed by all buses combined. The output of the problem is an integer, which represents the minimum time required to ensure that at least total trips are completed. For example, if time equals 1, 2, 3, and total trips equals 5, we need to calculate the smallest time t such that the buses collectively complete at least 5 trips. Let's look at specific examples to better understand how this works. For the first example, we have time equals 1, 2, 3, and total trips equals 5. The output is 3. Here's why: at t equals 1, the first bus completes 1 trip, while the other 2 buses have yet to start their first trip, resulting in a total of 1 trip completed. At t equals 2, the first bus completes 2 trips, the second bus completes 1 trip, and the third bus still hasn't started, making the total 3 trips. Finally, at t equals 3, the first bus completes 3 trips, the second bus completes 1 trip, and the third bus completes 1 trip, reaching the required 5 trips. Therefore, the minimum time required for the buses to complete at least 5 trips is t equals 3. As another example, if time equals 2, and total trips equals 1, the output is 2 because the only bus takes 2 units of time to complete 1 trip, matching the required number of trips. Now let's consider a slightly more complex example. If time equals 9, 3, 10, 5, and total trips equals 10, the output is 15. This is because, at t equals 15, the first bus completes 1 trip, the second bus completes 5 trips, the third bus completes 1 trip, and the fourth bus completes 3 trips, resulting in a total of 10 trips. It's worth noting that no smaller value of t would allow the buses to collectively complete the required number of trips. This example illustrates how different buses with varying trip durations contribute to the overall total at different times. The challenge is to determine the smallest time that ensures the total number of trips is met, regardless of how the trips are distributed among the buses. In this problem, several constraints and considerations must be taken into account. First, the number of buses, represented by the length of time, can range from 1 to 100,000. Each bus's trip time, represented by time, I, can be as small as 1 or as large as 10 million. Additionally, the required total number of trips, total trips, can also be as high as 10 million. Importantly, the time t is not provided as an input, it must be calculated. The solution must ensure that the sum of trips completed by all buses at time t is at least total trips, and the goal is to minimize this value of t. Special cases to consider include scenarios with only one bus, very large values of total trips, or cases where all buses have identical trip times. These edge cases highlight the importance of an efficient solution, as the constraints make brute force approaches infeasible for larger inputs. To start, let's consider a brute force approach to solve the problem. The idea here is straightforward: simulate the process step by step. For each time unit, we calculate how many trips each bus completes using the formula t/time I, where time I is the time it takes for the bus to complete 1 trip. By summing up the trips for all buses at each step, we can determine whether the total number of trips meets or exceeds the required total trips. If it does, we return that time as the solution. However, this approach has significant drawbacks. The time complexity is O, max time *n, where max time could be extremely large, representing the maximum time needed for any bus to complete all required trips. This makes the approach computationally infeasible for large input sizes, even though it has a constant space requirement. Because of its inefficiency, this method is not suitable for solving the problem at scale. Instead, we need a more optimized strategy. Now, let's explore the binary search approach, which is much more efficient. The key insight here is that the number of trips completed by all buses is a non-decreasing function of time. This means that as time increases, the total number of trips can only increase or stay the same, never decrease. This property allows us to use binary search to find the minimum time required to meet or exceed total trips. First, we define our search range. The lowest possible time is 1, and the upper bound is max time, asterisk total trips, which represents the worst-case scenario where a single bus handles all the trips. During the binary search, we calculate the midpoint of the range and determine the total trips completed at that time. If the total trips meet or exceed total trips, we adjust the upper bound to try for a smaller time. Otherwise, we increase the lower bound to search for a longer time. Once the search concludes, the lower bound will give us the minimum time required. This approach is far more efficient, with a time complexity of n asterisk log, max time, where n is the number of buses. It is both fast and space efficient, which is why it's the preferred method. The binary search approach is ultimately the chosen solution because it strikes the perfect balance between efficiency and simplicity. Unlike the brute force method, it avoids simulating each individual time step and instead narrows down the solution space logarithmically by leveraging the monotonic nature of the problem. This makes it highly scalable, even for large input sizes with high values of total trips or buses that take a long time to complete trips. The breakthrough insight here is recognizing that the number of trips completed is a monotonic function of time, which allows us to apply binary search effectively. This insight drastically reduces computational complexity, turning what would otherwise be an infeasible problem into a manageable one. In summary, the binary search approach is the optimal choice for this problem. It is efficient, logically clear, and well suited for competitive programming contexts where performance matters most. It guarantees correctness while ensuring that we can handle even the largest inputs within the given constraints. The goal of this problem is to calculate the minimum time required for a fleet of buses to complete a specific number of trips. Each bus has a fixed trip duration, and our objective is to determine the smallest time at which the combined trips from all buses meet or exceed the target number of trips. To start solving the problem, the first step is to understand how the trips are calculated. For any bus with a trip duration time, I, the number of trips it can complete by a given time t is simply t/time, I, which gives the integer division result. The challenge lies in finding the smallest time t that ensures the total trips from all buses are at least equal to total trips. Initially, we can consider a brute force approach, where we increment the time step by step, calculating the total trips at each step. If the total trips meet or exceed the target, we return the current time. However, this method simulates every time step and becomes computationally expensive for large inputs, leading to inefficiencies that we need to address with a more optimized strategy. The brute force approach, while simple, is not practical for large-scale inputs. Its inefficiency arises from the need to check every possible time step up to a maximum value, resulting in a time complexity of max time n, where max time represents the largest possible time and n is the number of buses. To overcome this limitation, we use binary search to significantly reduce the number of time steps we need to evaluate. First, we define the search space for the binary search. The minimum possible value for low is 1, as trips can't be completed in 0 time. The maximum possible value for high is calculated as max time total trips, which represents the worst-case scenario where only the slowest bus operates to complete all the trips. With this range, we iteratively narrow down our search space. At each step, we calculate the midpoint mid of the current range and determine the total trips all buses can complete by mid. This is done efficiently using the formula sum mid/time I for all I. If the total trips meet or exceed the target, we attempt to find a smaller time by updating high to mid 1. Otherwise, we explore larger times by updating low to mid +1. Once the binary search loop terminates, the variable low holds the minimum time required to complete the trips. This optimized approach leverages the efficiency of binary search, which reduces the search space logarithmically, making it far superior to the brute force method. A key insight here is the use of the formula t/time I to calculate the trips for each bus in constant time. This eliminates the need to simulate every single time unit, allowing us to compute the total trips in n time for each binary search iteration. It's also important to account for edge cases, such as when all buses have the same trip duration, when there's only one bus available, or when the required number of trips is extremely large. The algorithm handles these scenarios naturally due to the flexibility of the binary search framework. In terms of data structures, the input array time is used to store the trip durations for each bus, and we dynamically manage variables low, high, and mid to refine our search space. These components work together to ensure the solution is both time efficient and simple to implement. When analyzing the complexity of this algorithm, we find that its time complexity is O, n asterisk log, max time, where n is the number of buses, and max time is the upper limit of the search space. This is because we perform a binary search over the time range, which takes O, log, max time, iterations, and for each iteration, we calculate the total trips in O, n, time. The space complexity is O1, as the algorithm uses only a few variables for the binary search and does not require additional data structures. To better understand the algorithm, let's consider an example. Suppose the input is time equals 2, 3, 7, and total trips equals 10. We start by initializing low to 1 and high to 70, calculated as max time asterisk total trips. In the first iteration, the midpoint is mid equals 1 plus 70 / 2 equals 35. At this time, the total trips completed are 35 / 2 plus 35 / 3 plus 35 / 7 is equal to 17 plus 11 plus 5 equals 33. Since 33 is greater than or equal to the target of 10 trips, we narrow the range by updating high to 34. This process continues until low equals high, and the final value of low is 14, which is the minimum time required to complete the trips. The algorithm achieves its efficiency by focusing on two key operations. First, it computes the total trips for all buses at a given time using the formula t/time, I. This allows the algorithm to avoid simulating every individual time step, making the trip calculation highly efficient. Second, it uses binary search to narrow down the range of possible times logarithmically, ensuring that we only evaluate a small subset of potential values for t. To further optimize the algorithm, we can leverage the smallest trip time to refine the upper bound for high. For example, instead of directly using max time asterisk total trips as the upper limit, we could consider tighter bounds based on the distribution of trip times. In cases with extremely large inputs, pre-computing or reusing partial sums may also help reduce computational overhead. These enhancements make the algorithm robust and scalable, capable of handling a wide range of inputs efficiently. By combining careful calculation with strategic narrowing of the search space, the algorithm provides an elegant solution to the problem of finding the minimum time to complete trips. This solution uses a binary search approach to find the minimum time required for buses to complete the specified number of trips. The function minimum time takes two inputs, a list time where each element represents the time a bus takes to complete one trip, and total trips, the total number of trips required. First, we define a helper function can_complete_trips_in_time, t, which checks if all buses combined can complete at least total trips within a given time t. The function iterates through each bus's trip time, summing the number of trips each bus can complete, t/trip_time. If the sum reaches or exceeds total trips, the function returns true and stops further calculations for efficiency. The main logic involves binary search. The variable left is initialized to 1, minimum possible time, and right is set to the worst-case scenario where the fastest bus completes all trips alone, min, time, asterisk total trips. The binary search narrows down the range until left equals right, which is the minimum time required. In each iteration of the binary search loop, the midpoint mid is calculated, and can_complete_trips_in_time, mid, determines if the current time mid is sufficient to meet the trip requirement. If it is sufficient, the search narrows to the left half of the range, right equals mid, to find a smaller feasible time. Otherwise, it moves to the right half, left equals mid plus 1. When the loop ends, left holds the minimum time required to complete the trips. This approach ensures efficiency with a time complexity of O, n asterisk log, k, where n is the number of buses and k is the search range for time. This is efficient enough given the problem constraints. Here, we start by importing the necessary Java utilities and defining our solution class. The main method, minimum time, takes an array of integers time, representing the time each bus takes for one trip, and an integer total trips, which is the target number of trips we need to complete. To solve this problem, we use a binary search approach, but first, we define a helper method, can complete trips in time. This method determines whether we can complete the required number of trips within a given time t. It iterates over each bus in the time array, calculating how many trips each bus can complete within t by dividing t by the individual bus's trip time. If the cumulative trips meet or exceed total trips, the method returns true, stopping early to optimize performance. Otherwise, it returns false. Next, we establish the boundaries for our binary search. Left is initialized to 1, representing the minimum possible time, and right is set to the product of the smallest trip time and total trips, which represents the maximum possible time required if only the fastest bus is used repeatedly. Then, we enter the binary search loop. Inside the loop, we calculate the midpoint, mid, to divide the search space. If can complete trips in time returns true for mid, it means we might be able to achieve the target in less time, so we move the upper boundary right to mid. Otherwise, we adjust the lower boundary left to mid +1 to allow more time for the buses to complete the trips. Once the binary search loop completes, the left boundary will hold the minimum time required to complete all the trips. This value is then returned as the result. By leveraging binary search, this solution efficiently narrows down the minimum time by repeatedly having the search space, ensuring optimal performance even for larger input sizes. Overall, this approach balances precision and efficiency, making it well suited for solving the problem within the constraints. In this problem, we want to determine the minimum time required to complete at least 5 trips using buses with trip times 1, 2, 3. To achieve this, we use a binary search approach. First, we initialize our search range. The left boundary is set to 1, representing the smallest possible time to complete any trip. The right boundary is derived by assuming the fastest bus completes all 5 trips, which gives us min time * total trips is equal to 1 times 5 equals 5. Next, we enter the binary search loop. In the first iteration, we calculate the midpoint as mid equals 1 plus 5 / 2 equals 3. We then check if completing 5 trips is possible within 3 units of time. By dividing the time t equals 3 by each bus's trip time, we get 3 / 1 equals 3, 3 / 2 equals 1, and 3 / 3 equals 1, which sums up to 5 trips. Since this meets the requirement, we update right to mid, narrowing the search to right equals 3. In the second iteration, we recalculate mid as mid equals 1 plus 3 / 2 equals 2. This time, we check if 5 trips can be completed in 2 units of time. The calculations yield 2 / 1 equals 2, 2 / 2 equals 1, and 2 / 3 equals 0, totaling only 3 trips, which is insufficient. Therefore, we update left to mid +1 equals 3 and proceed with the search. When the binary search concludes, left and right converge at 3, indicating that the minimum time required to complete 5 trips is 3 units. This result is returned as the output. Now, let's explore a second example with the input time equals 2, 3, 7, and total trips equals 8. We start by initializing the search range. The left boundary remains 1, while the right boundary is calculated as min time * total trips is equal to 2 times 8 equals 16. With the boundaries set, we proceed with the binary search process. In the first iteration of the binary search, we calculate the midpoint as mid equals 1 plus 16 / 2 equals 8. We evaluate whether 8 trips can be completed in 8 units of time. The bus calculations yield 8 / 2 equals 4, 8 / 3 equals 2, and 8 / 7 equals 1, which totals 7 trips. Since this is less than the required 8 trips, we adjust the left boundary to mid +1 equals 9. In the second iteration, the new midpoint is mid equals 9 plus 16 / 2 equals 12. This time, we find 12 / 2 equals 6, 12 / 3 equals 4, and 12 / 7 equals 1, adding up to 11 trips. Since this meets the requirement, we update right to mid equals 12. Iteration 3 gives mid equals 9 plus 12 / 2 equals 10, with the calculations resulting in 10 / 2 equals 5, 10 / 3 equals 3, and 10 / 7 equals 1, totaling 9 trips. Again, this satisfies the condition, so we update right to mid equals 10. In the fourth iteration, we calculate mid equals 9 plus 10 / 2 equals 9, yielding 9 / 2 equals 4, 9 / 3 equals 3, and 9 / 7 equals 1, which gives exactly 8 trips. Since this is sufficient, we update right to mid equals 9. At the conclusion of the binary search, left and right converge at 9, indicating the minimum time required to complete 8 trips is 9 units. This value is returned as the output. Finally, consider a third example where time equals 5 and total trips equals 10. With only one bus available, we initialize the boundaries as left equals 1 and right equals min, time, asterisk total trips is equal to 5 times 10 equals 50. The first midpoint is computed as mid equals 1 plus 50 / 2 equals 25. This yields 25 / 5 equals 5 trips, which is insufficient, so we update left to 26. In the second iteration, mid equals 26 plus 50 / 2 equals 38, resulting in 38 / 5 equals 7 trips. Again, we adjust left to 39. The third iteration gives mid equals 39 plus 50 / 2 equals 44, with 44 / 5 equals 8 trips, prompting us to set left equals 45. In the fourth iteration, mid equals 47 yields 47 / 5 equals 9 trips, and we set left equals 48. Finally, at mid equals 49, we still have only 9 trips, so we update left equals 50. The binary search concludes at left equals 50, which is returned as the minimum time to complete 10 trips. To analyze the time complexity of our solution, we start with the binary search process. Binary search operates on the range from 1 to the product of the smallest time in the time list and the total number of trips needed. Let's denote this maximum range size as k equals min, time, asterisk total trips. Binary search reduces this range by half in each iteration, which means it performs approximately O log k iterations. Within each iteration of binary search, we use a helper function called can_complete_trips_n_time. This function evaluates whether all buses in the time list can collectively complete the required trips within a given time t. Here, the function iterates through the time list, performing an O(1) operation for each bus to calculate the trips it can complete using integer division. Therefore, the time complexity of this function is O(n), where n is the number of buses. Combining these, we see that binary search runs O log k iterations, and each iteration involves a helper function call with complexity O(n). Hence, the overall time complexity of the solution is O(n * log k). Now, let's examine the space complexity of the algorithm. The function can_complete_trips_n_time does not rely on additional data structures. It uses a few simple variables like trips, t, and trip_time, all of which take constant space, or O(1). Similarly, the binary search process itself operates using only variables such as left, right, and mid, which also require constant space. Additionally, the input list time is read-only and is not modified or copied during the execution of the algorithm, so it does not contribute to the additional space usage. When we combine these observations, we find that the algorithm does not require any extra memory beyond what is needed for a few variables. As a result, the overall space complexity of the solution is O(1). This makes the algorithm not only time efficient but also very space efficient. To understand why this approach is efficient, let's compare it to a naive or brute force method. A brute force approach would iterate through all possible times t from 1 to min, time, * total trips, checking for each whether the total number of trips meets the required total trips. For each candidate time t, the algorithm would iterate through the time array to calculate trips, resulting in a complexity of O(n k), where k equals min, time, * total trips. This is highly inefficient for large inputs. On the other hand, the optimized approach uses binary search to reduce the number of times checked from O(k) to O log k. By significantly narrowing down the search space, the binary search approach achieves an overall time complexity of O(n * log k, making it far more suitable for scenarios with large values of total trips in time. This demonstrates how binary search can transform a computationally expensive problem into a manageable one. Finally, let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, the required number of trips is achieved within the first few iterations of the binary search. However, because the binary search process still dominates the runtime, the time complexity remains O (n asterisk log k). In the average case, the binary search performs its typical O log k iterations, and the helper function is called at each step, resulting in the same overall complexity of O (n asterisk log k). Even in the worst case, where the algorithm explores the entire search range from 1 to min, time, asterisk total trips, the binary search completes in O log k steps, with each step requiring O n time for the helper function. Therefore, the worst-case complexity is consistent at O n asterisk log k. This consistency in performance is backed by the mathematical reasoning that binary search reduces the range logarithmically, while the helper function's cost per step grows linearly with the number of buses. Overall, this approach balances efficiency with simplicity, achieving O (n asterisk log k) time complexity and O(1) space complexity, making it highly effective for this problem. When solving this problem, there are several common mistakes to watch out for. First, in the brute force approach, many people make the mistake of incrementing time by just 1 unit. While this might seem logical, it leads to extremely inefficient solutions with a time complexity of O max underscore time, which becomes impractical for large inputs. Instead, you should increment by the smallest possible step that could affect the outcome. Another frequent issue is overlooking edge cases. For instance, scenarios like having 0 buses, only 1 bus with a high trip requirement, or buses operating at vastly different speeds can easily trip up an unprepared solution. A classic mistake is assuming all buses contribute equally, which is not always the case. Additionally, errors in setting binary search bounds are also common. If the lower or upper bounds are not chosen carefully, for example, setting the lower bound too high, you risk infinite loops or failing to find a valid solution. Finally, not pre-computing or caching values, such as the number of trips a bus can complete within a given time, can significantly slow down your program. This redundancy increases runtime, especially with large inputs, and is something to avoid for an optimal solution. Now, let's discuss the importance of understanding problem constraints and some insights to help you succeed in interviews. Misunderstanding the constraints, such as the limits on the number of buses or trips, can lead to overly complex solutions that fail to scale for large inputs. This is why analyzing constraints is so critical. A key takeaway is that binary search plays a central role in solving these types of problems. Many minimization or maximization problems can be reframed as decision problems, which binary search handles efficiently. Optimization techniques are another area interviewers focus on. While brute force might initially seem intuitive, demonstrating how you can refine it into a more efficient solution shows strong problem-solving skills. It's also helpful to recognize patterns. For example, problems involving scheduling or resource allocation often share structural similarities, and practicing these can help you identify solutions faster. Finally, remember to communicate your thought process clearly. Whether you're handling edge cases or debugging, a structured and methodical approach helps interviewers understand your reasoning and evaluate your problem-solving approach more effectively. There are several related problems that you should explore to deepen your understanding of this type of question. For example, LeetCode 1011, which involves determining the capacity required to ship packages within a certain number of days, shares similarities in its approach. Other examples include LeetCode 875, where you calculate the minimum eating speed for cocoa to finish bananas within a deadline, and LeetCode 1552, which involves maximizing the magnetic force between 2 balls. Problems like LeetCode 410, which focus on splitting an array to minimize the largest sum, also follow a comparable pattern. These examples reinforce the same core techniques, particularly binary search. Speaking of approaches, binary search remains the optimal solution here, with a time complexity of O (n asterisk log max underscore time, where n is the number of buses. While incredibly efficient, its success depends on implementing the decision function carefully. Alternatively, you can use a priority queue to dynamically assign trips to buses based on their availability. Although this approach is more intuitive, it tends to be less efficient for large inputs compared to binary search. Finally, another approach you might consider is leveraging mathematical analysis. In certain cases, you can derive a direct formula or heuristic to calculate the minimum time required based on the constraints of the problem. This can lead to highly elegant and efficient solutions, but it comes with its own trade-offs. Specifically, these methods are often limited in their applicability and may require a deeper understanding of the mathematical principles underlying the problem. While not always the go-to method, exploring this avenue can sometimes reveal insights that improve both your understanding of the problem and your ability to solve similar ones in the future. To wrap up, we reviewed the minimum time to complete trips problem, summarized the binary search-based approach, and discussed its time and space complexities. Remember, binary search is a versatile technique for optimization problems, so practice similar challenges to strengthen your skills. Thanks for tuning in, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!